In this video, we're going to discuss the basic ideas of equilibrium. Normally, when we've seen balanced reactions before, we'll see something like methane plus 2O2 becomes CO2 and water, two of them. When this is done on your stove at home, reasonably, you see all the methane burn, makes carbon dioxide, and makes water. We even draw the arrows saying, hey, we become these products. However, this is not really what's happening. A one-direction reaction is uncommon. Some reactions are so good at doing what they do that it seems that 100% of things will convert. However, it's easier to see with some other reactions that in reality, we don't go all the way to products. In the Haber-Bosch reaction, N2 and 3 H2s will become 2 NH3s. However, 2 ammonias, 2 NH3s, can also break into N2 and 3 H2, which is just the reverse reaction. Some reactions, your reactants can make products, but your products, well, they're chemicals. There's no reason they cannot also react, and it's possible they can react with themselves to go backwards, to go back to the starting material. Really, the starting materials are just product of the reverse reaction. What this means, though, is that reactions can actually go in both directions. Your starting materials can become products, and your products can become starting materials. And the truth is, every reaction can do this. Some are so unbelievably one-sided that it looks like they're one direction. However, many others, it's far more obvious that both are actually occurring. How does this change how we think about reactions? Well, it changes the amount of product you'll make. If you try to calculate your theoretical yield and you assume 100% of your starting material will convert, but in reality, plenty of it won't because it goes back to being starting material, then you can never obtain as much product as you think you could from those theoretical calculations. What's causing this? What does equilibrium represent if our reaction can go both directions? Well, that you'll really have a mix of products and reactants. Reactions never really reach completion. There's always a mix of products and reactants. Sometimes they're fairly close in value, sometimes they're billions of times different. But there's always theoretically some products and some reactants. Because of this, well, we have to think of the two directions. If you think of a rate for the forward direction, well, it's going to be equal to some constant of reaction forward times the concentration of the reactants. If we assume a simple elementary step reaction, such as N2O4 in equilibrium with 2NO2. The forward reaction is just one molecule breaking. The reverse reaction is two molecules impacting to form one. So there's a rate forward in this example that's equal to a constant forward times the concentration of the starting material for that reaction. Well, the reverse reaction is equal to a constant for the reverse times, well, in this case, as written, the products, but the reverse reaction, those would be the reactants. So however much NO2 is available is going to determine the reverse rate. So NO2 squared in this assumed elementary step reaction. If initially we have no NO2, then the only thing that can happen is we do the forward reaction. So for a while, we'll do the forward reaction. Over time, we'll build up some product and we'll start doing the reverse reaction. As we get more and more product, we'll get more and more reverse reaction. We'll end up using up some of the starting material and we'll see its rate slow down as N2O4 decreases. Eventually, from the decrease in the starting material N2O4, our rate will get lower, and the increase in our product means the reverse rate will get faster. At some point, these two will be equal to each other. There will eventually be a point where the rate forward is equal to the rate reverse. When this is finally reached, we can no longer see our concentrations changed. Early on, we saw a decrease in the N2O4 because it was making the product, and there was no product to go backwards. And so our product simply increased from 0. But as it built up and could react to go backwards, and as our starting material decreased in amount so it couldn't react as quickly to go forward, eventually those reached some concentrations where their rates were equal to each other. This occurs at equilibrium. While we are at equilibrium, because our rates are equal forward and backward, whatever amount of starting material would be used up per second, just that same amount of starting material is created per second in the reverse reaction. As a result, concentrations no longer alter. For a given reversible reaction, there will be some concentrations of product and reactant where the rates forward and reverse will be equal, and that concentration will then remain indefinitely. This is a dynamic equilibrium. Any one molecule, or two molecules if you're products, can indeed react and change into the other side of the equation, but the same amount will be happening in both directions, so the overall quantities will not alter. Equilibrium reactions are extremely important in things such as biology, as they maintain homeostasis. If your bloodstream begins to lose sugar concentration, well, then the enzymes that normally store it can't find it to store it. At the same time, the ones that normally release it continue to release it and replace it. When you're at your optimal blood sugar level, they're pulling out and replacing at the exact same speed, so the concentration in your bloodstream doesn't alter. But if you start running, your blood sugar plummets as your muscles use it. It then starts getting replaced without nearly as much being removed. On the other hand, if you ingest a great deal of sugar, suddenly there's way more to be obtained to pull out, and the enzymes that pull it out of your bloodstream are able to do so more readily. It increases the rate of removal. But the enzymes breaking it free from storage aren't changed by it, and so you favor removing until you're back down to your equilibrium concentration. Because the rates are affected by the concentrations, even as our concentrations alter, they will then continue to change over time until the rate forward and rate reverse are then equal again. All equilibrium reactions will eventually return to equilibrium. Let's look at that numerically really quick. Imagine I had 100 reactants and 10 products of whatever these compounds are, A and B. Let's give ourselves some simple K value. We'll say that the K forward is 0.1, while the K reverse is 0.3. And the rate is just equal to the K times the concentration. If that was the case, in our first time unit, we'll say per second or whatever it is, our concentration is going to change. We're going to lose some of our A. How much? Well, 100 times 0.1. We're going to lose 10. And our reverse reaction is going to happen. How much? Well, 10 times 0.3, so 3. After this occurs, we're going to have some new concentrations of each chemical. A lost 10 but gained 3 for a difference of 7 being lost, so it's going to be down to 93. B lost 3 but gained 10 for a net increase of 7 to be at 17. That is the forward reaction. I just had way more of compound A, so more of it's able to react, even if its K value is a little smaller. Well, time 2, our new concentrations are reacting instead. Same idea is going to happen. Well, it was originally 10 and 3. I've got new concentrations, and so my forward reaction is going to be 0.1 times 93 for 9.3 change. My reverse is going to be 17 times 0.3 for a 5.1 change. That difference here is 4.2. For simplicity, we'll round to just 4, which means we're going to lose 4 from our concentration of A and go down to 89. We're going to gain 4 for our concentration of B, as more was heading towards B than leaving. We'll go up to 21. And process would repeat. You'd go to time 3. Your new change will be 8.9. Change here, 6.3. For a difference of 2.6. And what we see is that each time unit, we're seeing a smaller and smaller difference. Our rates are getting closer and closer. They were originally separated by 7, then 4.2, then 2.6. This will continue until the difference is effectively none. At some point, our concentrations will have altered until the rate forward and reverse is equal. Whatever concentrations we reach at that point, that is the equilibrium concentration. That is the concentrations which will be maintained indefinitely until we disturb the reaction in some way. How we can do that will continue in other videos. But this is the idea of equilibrium. It is an emergent property from the idea that as the starting material gets used up, the rate forward will get slower. As product is formed, the rate reverse will get faster. At some point, those two rates will be equal and no changes can therefore occur after that.